I'm going to go over the study questions for Chapter 19. Now these questions are good because they go through all the main ideas that show up in Chapter 19. But a big thing here is to go ahead and try these problems first and then view this tutorial. I wanted to pick out a nice picture of a precipitate, and this one is very good because it has this lead iodide. And of the little kind of pieces of trivia you're supposed to know, you are supposed to know that lead iodide does come out to be a yellow precipitate. So you might want to just tuck that away in your brain, that PbI2 is a yellow precipitate. The first question we go through is predict on the basis of the solubility rules which of the salts are soluble and which are insoluble. And for the insoluble ones, they want you to look up the solubility products. So that's no big deal. So for each one, we say A. This is AgI. We know that iodide, chloride, and bromide are soluble except for silver, lead, and mercurous. So silver iodide would be insoluble. Barium sulfate. I jumped to C here. Okay, sulfates are soluble except for calcium, barium, strontium, and lead. This is just our solubility rules. And carbonates over here, nickel carbonate. Carbonates are almost always insoluble except for the alkaline metals, and that's about it, and ammonium. So far those three. Next one here, sodium phosphate. Okay, we know that sodium compounds are always soluble, so we can eliminate that. Ammonium sulfate, we know that ammonium compounds are always soluble. And hydroxides are almost always insoluble. So copper, the only ones that would be soluble are the alkaline metals and calcium, barium, strontium. So we have 4 of these that are insoluble. Now your job would just be to look up a table of KSPs, and we would find out that things like AgI is 1.5 times 10 to the negative 16, and BaSO4 is 1.1 times 10 to the negative 10. Nickel carbonate 6.6 times 10 to the negative 9. And finally copper hydroxide 1.6 times 10 to the negative 19. So these numbers are pretty small because not very much of the stuff dissolves. Now I'm going to write the solubility product expression for each of these, and this just exactly follows what we learned for different equilibrium. So lead sulfate, the KSP, is the concentration of lead times the concentration of sulfate. And the reason it comes out like that is we're saying lead sulfate is a solid, and it breaks up to give lead ions, aqueous, and sulfate ions, aqueous. So when we write the KSP, it's simply going to be lead ion concentration times the concentration of sulfate ions raised to the first power, because these are 1 and 1, and the solid does not enter into the expression. So there's our solubility product expression. Now when we get to letter B, we can see that we have 3 calciums and we have 2 phosphates. So when we write the ions, we're going to get calcium 2 plus 3 of those, and PO4 2 minus 2 of those. So our KSP, concentration of calcium ion to the 3rd power, concentration of phosphate squared. For our next one here, we have a copper sulfide. We're going to get a copper 2 plus ion and an S2 minus ion. So we can see what's going to happen is we'll have KSP is equal to the concentration of copper 2 plus times the concentration of sulfide 2 minus. In our last example, we can see we have calcium fluoride, so the KSP will be concentration of calcium ion, Ca2 plus, concentration of fluoride ion squared. Notice that the in-between step for each one of these would be to at least visualize, if you don't write it out, what the equation would be. And each of these is a solid breaking up into its ions. Now, this one says, if the molar concentration of lead bromide happens to be 1.6 times 10 to the negative 6 molar, then what's the lead concentration? And what's the bromide concentration? Now this is really a very simple problem. It's the idea that in one lead bromide, every time you dissolve it, you get one lead and you get two bromides. So this would be the situation if we had, let's say some kind of a sandwich. Okay, let's say it's a bologna sandwich. And then on that bologna sandwich, we might have 2 pieces of bread. So if we had 16 of these bologna sandwiches, we'd end up with 16 pieces of bologna. And because there are 2 pieces of bread, we're going to have 32 pieces of bread. So the same thing, if I have 1.6 times 10 to the minus 6 PBBr2s, then when I get to my lead ion, since there's one lead ion in every PBBr2, it's also going to be 1.6 times 10 to the minus 6 molar, just the same number. But when I get to the Br minus, since there are 2 of those, I'll have 3.2 times 10 to the minus 6 molar. Very easy kind of a problem. But a useful idea, we're going to need that as we set up our KSP expressions. Now, if the molar solubility of silver iodine is 1.22 times 10 to the minus 8, now we've called that before. We said that's going to be our solubility, and that is the amount or the concentration of a solution that we could make. And it's a small number because we're saying, silver iodide is one of our insoluble compounds, but we know even if they say it's insoluble, it dissolves a little bit. So this is the most concentrated solution we could make. Now for AgI, we know that that is a 1-to-1 compound. There's one Ag and there's one I, and we figured out before that KSP is equal to solubility squared. So now this is just a simple algebraic problem. If the solubility is 1.22 times 10 to the minus 8, we want to find what is the KSP. So the KSP is simply going to be 1.22 times 10 to the negative 8 squared. Now we figure that's going to be 10 to the minus 16 for the answer, and 1.22 squared, it's about 1.5. Now officially, if somebody asks what are the units, since this is molarity and molarity, solubility is a molarity, then this is officially molarity squared, and a lot of times for the K values we just don't bother with the units. Okay, what is the molar solubility of cadmium sulfide if its KSP equals 3.6 times 10 to the minus 29? So this time we're saying, well, we know the KSP, we want to know what the solubility equals. Now CDS, cadmium sulfide, is a 1-to-1 compound, so we know that the KSP equals solubility squared. So our job now is just to take the square root. So we saw 3.6 times 10 to the negative 29 equals solubility squared. So the solubility will be the square root of solubility squared. And we can actually do this one in our head, because we say, well, this right, that is 36 times 10 to the negative 30. That's pretty easy. We know that the square root of 36 is 6. And the square root of 10 to the minus 30 is 10 to the minus 15. Now in this case we would put a unit on it because we know that molarity is a concentration. So the most concentrated solution of cadmium sulfide we could make is 6.0 times 10 to the minus 15. On question 6, the KSP of strontium fluoride is 2.5 times 10 to the minus 9. What's the strontium ion concentration and fluoride concentration in a saturated solution? Okay, now all of these KSPs we're talking about, the equilibrium situation is a saturated solution, a situation where everything that can dissolve has dissolved. And we're asking for what's the molar solubility as well. Well, for me, I actually like to answer the second question first. Because I have a strontium fluoride, we know that's a 1 to 2 compound. And from our earlier discussion, we know that the KSP for a 1 to 2 compound is 4s cubed. Now that came because of the fact that when that breaks up, we know that we have S for the strontium, we have 2s quantity squared for the fluoride, and that comes out to be 4s cubed. So if I know that the KSP is 2.5 times 10 to the negative 9, and that equals 4s cubed, then all I have to do is a little algebra, divide both sides by 4, and then take the cube root and for that I'm going to need my calculator, so I'll be right back. Okay, doing this with my calculator, I find out that the solubility here is equal to 8.6 times 10 to the negative 4 molar. So my solubility is the concentration of strontium fluoride, and I can go back now and say, well, what about strontium? Since there's only one strontium in every strontium fluoride, that's also 8.6 times 10 to the negative 4 molar. And since there are two fluorides, then it must be double that number, and that would be about 1.7 times 10 to the minus 3 molar. Now, question 7 says, what is the magnesium ion concentration in a saturated solution of magnesium fluoride? And the solubility product here is 6.4 times 10 to the minus 9. And it also asks, what's the magnesium ion concentration if it contains some sodium fluoride? So we have two different problems here. Well, the first one is, magnesium fluoride is a 1 to 2 compound, so therefore we know that the KSP is equal to the solubility, the KSP is equal to the 4 times the solubility cubed, 4s cubed. And if I know the solubility of MgF2, since there's one magnesium each one, then the concentration of magnesium ion is going to also equal the solubility. So all we have to do is take 6.4 times 10 to the minus 9, divide by 4, and take the cube root. That'll take me a moment. Okay, so getting my calculator, I find that the solubility here is 1.2 times 10 to the minus 3 molar. Now all I had to do was take my value, 6.4 times 10 to the minus 9, and divide by 4, and then take the cube root. That's the solubility and the magnesium ion concentration. If they asked for fluoride, I would have had to double that number. Now the second part of this, though, is different, and that is, what's the magnesium ion concentration if the solution also contains some sodium fluoride? Of sodium fluoride, we don't care about the sodium, that's a spectator ion. We care about the fact that this solution already has fluoride. So for this, I'm going to go back to the original equation, and we're saying that we have magnesium fluoride, solid, and that breaks up to give magnesium ions and some aqueous fluoride ions. Now, when we do our solubility of this, we usually say, okay, well, we don't care about the solid here, but we do care because this is where we're going to define our solubility. And solubility is the amount of magnesium fluoride that would dissolve. So I'm going to put in, S for solubility, and that's the amount of magnesium fluoride solid that would dissolve. And over here I would say that this is 0, and I would say fluoride is 0 if I'm doing my normal solubility. But in this case, we have a little bit of our fluoride. So this actually is 0.30 molar way over here. So here's a situation where we're starting with some fluoride in our solution, and we can kind of see that this is called the common ion effect, because magnesium fluoride and sodium fluoride have fluoride in common. So it's called the common ion. After that, it's just a really standard sort of icebox. So if this is negative S, this will be positive S and positive S. So this will be S, and it will be 0.3 plus S. Now the situation is S's, we know are not very big. In this case here it was 1.2 times 10 to the minus 3 if we tried to dissolve magnesium fluoride in pure water. But if we try to dissolve that in something that's got fluorides already, that is going to shift the equilibrium back to the left, which means our S is going to be even smaller than it was before. So we're going to find out that we can make the assumption that X is much smaller than 0.3. So therefore, 0.3 minus plus S is really going to be about the same as 0.3. So if we could fit in here, and this is going to be tight, our KSP expression, it's the concentration of magnesium times the concentration of fluoride squared, and I'm going to say S for magnesium. I'm going to say 0.3 squared for my fluoride. Then we can calculate, and I already know the KSP is 6.4 times 10 to the minus 9. I know that I have 0.3, so I just have to solve for my solubility. And I'm going to do that and come back. Okay, I've calculated that, and I really have no room to show that, I'm sorry, but it does come out to be 7.1 times 10 to the negative 8 molar. So we can see what happens is, if you try to take magnesium fluoride and just dissolve it in pure water, we get a value of 1.2 times 10 to the minus 3, and we can do that with our formula. But if we want to find out, well, what if we try to dissolve it in a solution that already has some fluoride in it, then we get a much smaller number, because the chances of magnesium and fluoride bumping into each other and turning back into magnesium fluoride is much greater, so very little is going to dissolve, and our solubility becomes 7.1 times 10 to the negative 8, which is 10,000 times less concentrated. Now back on number 8, which of the following mixtures of silver nitrate and sodium sulfite would silver sulfite precipitate? We have the KSP for silver sulfite. Now this problem actually has parts A, B, and C. I'm only going to do A and leave B and C for you to do. So what happens here is we're saying the KSP for silver sulfite is a tiny number, 1.5 times 10 to the minus 4. And we could write the KSP expression for this. We know that silver is Ag plus, and sulfite SO3, 2 minus. And if we wrote the equation, we would have 2 Ag pluses and 1 sulfite, so there's a 2 up here. Now, in a saturated solution, the amount of silver ion squared times the concentration of sulfite ion will equal 1.5 times 10 to the minus 4. And our big thing is, if we put in a different number, a different amount of silver and sulfite, will we have enough ions to saturate the solution and form a precipitate, or do we have such small numbers here that it ends up all dissolving? So what we're going to do here is go back to an idea we saw before, and that's Q. And Q, we're just going to take the concentration of our silver ion squared times the concentration of our sulfide ion, and if that comes out to be greater than our KSP, we're trying to put in too many ions, we get a precipitate. If it's smaller than the KSP, then everything is going to dissolve. So now all we need is the concentration of silver ions, and we need the concentration of sulfide ions from the information. So if we have 50 milliliters of 1 times 10 to the minus 4 molar silver, we do not have 1.0 times 10 to the minus molar silver ions to use in our expression. And the reason is, if we add 50 milliliters of this solution and 50 milliliters of any other solution, we just double the volume. And if we've doubled the volume, we've diluted our concentration. So to get our value, all we say is we have 50 milliliters of 1.0 times 10 to the minus 4 molar. But since we've diluted, we're going to divide by our new volume, which is 100 milliliters. And I got that by doing 50 plus 50. So my concentration is 50 over 100 times 1.0 times 10 to the negative 4. So the value I actually have is 0.5 times 10 to the negative 4 molar, or I could write that as 5 times 10 to the minus 3 molar. No, that's not right. 5 times 10 to the minus 5 molar. But 0.5 times 10 to the minus 4 molar is fine. And you can see, since this is the same concentration, this is going to come out to the same. And when I do 0.5 times 10 to the minus 4 molar squared times 0.5 times 10 to the negative 4, then I get a value of 1.25 times 10 to the negative 13 molar. So that's my value of Q. Going back and comparing, I can see this is 1.5 times 10 to the minus 14. This is we can round that off to 1.3 times 10 to the minus 13. But, this is 10 times too large. So we say that my Q is greater than my KSP. So therefore, I'm definitely going to get a precipitate. Because I'm trying to put too many ions in solution, it'll totally saturate the solution, and the extra ions will turn into a precipitate. So in this case, I will get a precipitate. Yes. Okay, on part B, we do the same kind of situation. We have different numbers. So again, be careful about getting your dilution. You're putting together 50 milliliters and I don't have the numbers here anymore. Okay, so when you put those together, be sure and put it over the total. So the volume you have divided by the total volume times your concentration, and you'll find out what happens. Now in number 9, calculate the solubility of cobalt sulfide in a solution that already contains cobalt, in this case cobalt chloride. But we don't care about the chloride because chloride is not part of our KSP expression. So we have the KSP, and that's going to be the concentration of cobalt times the concentration of sulfide, and it has a value of 5.9 times 10 to the negative 21, small number. Now cobalt sulfide breaks up to give cobalt ion and sulfide ion, and we can make ourselves a little ice box. And we can see that again, this is a common ion effect because we have cobalt sulfide and we have cobalt chloride. They both have cobalt in common. So my value I will start with here is sulfide is 0, but my cobalt is 0.030 molar. So I'm going to define my solubility and say plus S. This will be S This will be 0.03 plus S. Now we're going to go ahead and assume that S is much smaller than 0.03, therefore 0.03 plus S will be almost exactly the same as 0.03. So we'll go back and put the numbers back in our calculator here. We'll say we have cobalt ion is 0.03 molar. The sulfide ion is going to be S, or solubility, and that equals 5.9 times 10 to the negative 21. And all we have to do is solve for S. Okay, that value comes out to be 2.0 times 10 to the negative 19. Now that would be the solubility of cobalt sulfide. That would also be my concentration of sulfide, and the concentration of cobalt is basically 0.03 because it's coming from the cobalt chloride. But my solubility is 2.0 times 10 to the negative 19. Common ion effect. Okay, the last problem is a little bit different, and this is if we were to put a strong acid into these solutions, and again these are probably have low solubility, which ones of these would increase the solubility? And the idea is if the negative ion, if the anion comes from a weak acid, then what it's going to do is to affect the pH of the solution, because that will be the conjugate base. Let's take one example and see what happens. Let's just take cadmium sulfide. So cadmium sulfide would break up and we get a little bit of sulfide, but we know what happens is sulfide ions will mix with water, and by hydrolysis will form a little bit of either HS minus or H2S and some hydroxide ions. So this is going to cause some hydroxide ions. But we can see what happens is if we put a strong acid in, that is going to lower the amount of hydroxide in solution, and that's going to shift this equation, shift the equilibrium to the right, and so our sulfide ion is going to go down. So if my equation here is cadmium sulfide solid is breaking up to be cadmium ions and sulfide ions, well, if I can remove more sulfide ions, then that's going to cause this will shift to the right and my solubility will increase. So if the sulfide ion, if the negative ion comes from a weak acid, it will do hydrolysis. If I add an acid, it removes my hydroxide, shifts this equilibrium to the right, which lowers my sulfide and shifts this equilibrium to the right. So any insoluble substance that has a negative ion from a weak acid is going to be a little bit more soluble in a strong acid solution. So we can go back and look. Okay, the sulfide, that comes from a weak acid. Okay, but not chloride. Chloride is from the strong acid HCl. Okay, sulfate comes from the strong acid H2SO4. But carbonate comes from the weak acid H2CO3. Going down here, bromide comes from the strong acid HBr. But hydrogen phosphate would come from the weak acid phosphoric acid. Cadmium hydroxide would come from the very weak acid water. And chloride, we get that out of there, that's from the strong acid HCl. So if we can see that the negative ion, that's the only part we have to concentrate on, the negative ion comes from a weak acid, or it doesn't come from a strong acid, then if we have a strong acid solution, that will increase the solubility of that substance.